Directions. Which of the series converge and which diverge? Give reasons for your answers. If the series is a geometric series, find the sum, if it converges, of course. There are several tests available to use: geometric series, p-series, nth term test, limit comparison test, direct comparison test, integral test, ratio test, and root test. You must use every test at least once. All right, number 10, so please don't think in these ones, if you used a different test than me, that it's wrong. Right, this one I did notice that it would be a p-series. However, we need to have terms that are all positive. So the first thing that I did, I rewrote this and I just bumped the -5 out front. So now this is a p-series and p equals 1, so the power is 1. And so since I could say since p is less than or equal to 1, the series diverges. Okay, number 11, the sum of n equals 1 to infinity of 1 over the square root of 3n minus 2, although there would be more than one way to work this one. I chose the integral test on this one. So I will be taking the integral from, and I should check the terms of the series, and it right after 1 it started decreasing, so I was fine. This is going to go from 1 to infinity of 1 over the square root of 3n minus 2. And then please remember on this one we can't actually approach infinity, so we're going to find the limit as w approaches infinity of 1 to w of 1 over the square root of 3n minus 2. And then from here I did a u substitution. I let u equal 3n minus 2. And then du was equal to 3. So I'm missing the 3 on the inside, so I did have to put a 1/3 on the outside. And then when I did that, this ended up being 1/3 over 1 over the square root of u, which is really 1/3 the integral of u to the -1/2. And if I added 1 to my power and divided by or multiplied by the reciprocal, I end up getting u to the 1/2 times 2, but there's a 1/3 sitting out front, so my integral is now going to be 2/3 the square root of 3n minus 2. I'm going to evaluate it at w and 1. So if I plug in w, I get 2/3 the square root of 3w minus 2, and then minus 2/3 the square root of 1, and this ends up being 2/3 the square root of 3w minus 2 minus 2/3. And since I'm as far as I can go, I'm going to find the limit as w approaches infinity. So if I put infinity in here, the square root of infinity is still going to be infinity. This will equal infinity. So I know that my answer is going to diverge. And if I wanted to be fancy, I could say since the integral from 1 to infinity of 1 over the square root of 3n minus 2 diverges, then the series also diverges. All right, problem 12, the integral of, the series n equals 1 to infinity of 1 over n squared plus 1. Again, I would say the direct comparison test actually would work quite nicely on this one. However, I chose once again to do the integral test. I saved my direct comparison test for a different one. So once again, I use the integral test. So I'm going to take the integral from 1 to infinity. And again, I did check my terms. And starting with 1, the sequence decreases, so I'm good to go. 1 over n squared plus 1, and obviously I can't actually go to infinity, so I'm going to be finding the limit as w approaches infinity of 1 to w of 1 over n squared plus 1. I then noticed that this was an arctan problem, and the u in my arctan is n, du is 1, and a is also 1, so it's all set up. So this will be 1 over a, which would just be 1, arctan u over a, which would just be n, and we are going to evaluate it at w and 1. So here I'll get arctan w minus arctan of 1. This will reduce to arctan of w minus the arctangent of 1. Where does the tangent equal 1? That would be at pi over 4. And that's as far as I can go. So now I'm going to find the limit as w approaches infinity. And then if I let this approach infinity, arctan of infinity, that means where does the tangent approach infinity? And I know the tangent approaches infinity at pi over 2. So this is going to be pi over 2 minus pi over 4, which equals pi over 4. And since I did get a finite limit, this is going to converge. So I can say since the integral from 1 to infinity of 1 over n squared plus 1 converges, so does the series. All right, and again, if you weren't sure, if you couldn't remember what arctan of infinity was, then using the direct comparison test would get you out of that pickle. All right, number 13, we've got the series n equals 1 to infinity of n plus 1 over 2n minus 1. Although there's, again, more than one way to work this, I decided that this was a good nth term test problem. So I'm going to be finding the limit as n approaches infinity of n plus 1 over 2n minus 1. And if I found that, I'd get infinity over infinity, which leads me to get to use L'Hopital's rule. And so if I took the derivative of the numerator and the denominator, I'm going to get 1 over 2. And so then my limit does equal, this should be the limit, sorry, as n approaches infinity of 1/2, which obviously equals 1/2. And with the nth term test, if we get a limit that does not equal 0, we know that our series will diverge. Okay, number 14, we have the series n equals 0 to infinity of e to the negative n. I decided on this one, I didn't see any others that looked like they would be a good geometric series, so I actually rewrote this without a negative exponent, and it looked like 1 over e to the n, which could be easily rewritten as 1 over e to the n power. So I did notice that this was a geometric series. And if I started writing the terms of the sequence on this one, we're starting at n equals 0. So when n equals 0, I'd get 1. And then when, excuse me, when n equals 1, I'd get 1 over e. And then when n equals 2, I'd get 1 over e squared, 1 over e to the third. So I noticed that my first term was 1, and my ratio is actually going to be 1 over e. And 1 over e is definitely less than 1. So since my ratio is less than 1, the series will converge. And on these problems, it did say if the geometric series converges to find the sum. So if you recall, the sum is equal to a over 1 minus r. The first term we found when I wrote out the series was 1, and then the common ratio was 1 over e. So this would be, if I got a common denominator, it would be 1 over e minus 1 over e. And if I then multiplied by the reciprocal, excuse me, I end up getting e over e minus 1. So that is my sum. All right, problem 15. This one, because of the way that it's set up, I do see some, actually on this one, there's a couple of different ways we could do it. We definitely could do a root test. I noticed since there was a I did notice since there was a plus sign, I decided to separate it into two separate series problems. So this will go n equals 0 to infinity of 1 over 5 to the n. And then this one would be n equals 0 to infinity of 2 to the n plus 1 over 5 to the n. And actually, I could use the ratio root, or what I'm doing now would work great. I'm going to just go ahead and stick with what I have here. I did notice that on this one, this would be a geometric series. I could rewrite it as 1/5 to the n. And then this one I could rewrite as, if I rewrote this, this is going to be 2 to the n times 2 over 5 to the n. And then I could rewrite this as its own little fraction. So I get 2/5 to the n times 2. So I actually did notice that these are both geometric series. And again, in either case, I think you'd have to separate it, but then you could use the root test or the ratio test just as easily. So on this one, I did notice that my first term, if I plugged in 0, would be 1. My second term would be 1/5, 1/25, and so forth. My ratio on this one would be 1/5. And then on this one, which is less than 1, so this one's going to converge. This one, again, my first term would be 2. My second term is going to be 4/5. My third term is going to be 8/25, and so forth. So I did notice on this one my ratio is going to be 2/5, which also is less than 1. So since in each case r is less than 1, the series is going to converge. All right, and then to find the sum, we'll find each one separately. This first one was a over 1 minus r. The first term is 1 over 1 minus 1/5, so that will be 1 over 4/5. So the sum of that series will be 5/4. And then the next one I'll have the a, which is 2 over 1 minus 2/5. That will give me 2 over 3/5, which is 2 times 5/3, which is 10/3. And then if I add 5/4 plus 10/3, I will get 55/12 will be my sum.